So welcome everyone. I'm very excited for everyone to be here. This is a very interesting topic on cross-institutional modeling and analytics. This is of high priority for Unizin, and it's something that is a gold mine, I think, for learning analytics and learning science. And it can be it's no small feat to get cross-institutional work done. So it's very excited to hear from Christopher and his team on some of the progress that they've been making. So with that, I'll hand it over to Christopher Brooks from University of Michigan to facilitate further introductions and get us going.
Great, thanks, Kyle. So yeah, let's talk about team first. I think of these fine institutions and people involved, I asked if I could present, being part of the Unizin consortium and having spent a lot of time with different Unizin folk over the 5, 6, 7 years of Unizin. But let me introduce the people who've been involved in this project. I want to call out Josh Gardner. He might be on the call at the University of Washington. He's a PhD student. What really shines is his brilliant work as a master's student at the University of Michigan, of course, but he's really been quite the driver and leader of a lot of this work and is extremely interested in educational predictive models and fairness. I also want to call out Renzhe Yu, who's just finishing up at the University of California, Irvine, his PhD, who has been working on this as well. Rene Kizilcec at Cornell University, who's faculty there, and then myself. I also want to call out Google and thank them. I didn't toss their logo up here, but Google actually gave us a little bit of discretionary funding for this project as seed funding, and it's been extremely helpful and useful. And what I'm talking about here today, the cross-institutional transfer learning for educational models, is work that is ongoing. We have sort of a draft of a preprint in this space. We have some results. Hasn't all gone through peer review. There's nothing to cite yet. So I'm sharing this with you all as a peek into what's happening, what we're doing with predictive models. And I'm especially invested in the opportunities that Unizin has to empower this work even further and make good use of it. Okay, so I just want to set a little bit. I know it's likely a diverse audience, and I want to set just a couple of ground pieces here. So when I talk about predictive models of student success, I'm being both broad and narrow at the same time. So I'm talking about statistical models that have been trained through historical data. That's very different than doing like a literature review and coming up with some ideas about what's going to predict success. Not that that's not data, but often that's not as much of a statistical model that is trained tightly with the historical data. We're also interested in predicting individual student success outcomes, and we're going to have a specific outcome that our experiments here have been on, but our whole team is interested in much broader sense of what student success is and how we can predict that. I'm going to be talking about our models which are trained through supervised machine learning processes. So this is an automatic mechanism once you've set it up. And really the intention of these models is to feed academic tools and processes to change student success for the better. Dashboards, advising, email interventions, etc. We are a group of computer scientists, informaticians, ed folks, and we're focusing on the prediction aspect. So I'm not going to talk about interventions. We've done some interventions, but not tied to this work, and isn't the focus here. These things require teams, and I'll talk a bit about that. So for those who may be less familiar with what the predictive modeling process looks like, I'm just going to share 4 steps here. First, you define what is success. So is it re-enrollment? Is it grade achievement? Is it time to degree completion? So undoubtedly, there are many, many, many more different measures of student success. Often in the literature and in academic communities, grade achievement has been used as the predictive outcome. But for many of us, that's actually not interesting as something like attrition at the end of a first year experience and not coming back into second year, or spending 6+ years at time to degree completion, because our interventions there can be quite different and are of high importance, I think, to us as institutions. The next step, after you've got some ideas of what success you're looking to enable, is to determine what you actually need to know to do this. So, and when you need to do it. So some of the early work in the area of educational data science and learning analytics looked at predicting grades, but they would often use most of the data for the semester, and that's just not useful once you come to the final exam. It's really too late to do anything about it. And so you really need to have this sense of temporal aspect to your predictions. When is it timely to get the prediction? How strong is it? Because if you just keep waiting and collect more data, your prediction accuracy or fitness will go up, but often it's too late to do something about it. Then the third step is look at your historical academic data and create statistical models. So what we tend to see in the literature is student information systems data, LMS data, things like the Unizin data warehousing platform, and so forth. But there's been lots of interesting work with different data sources, and we all come from different campuses that have different kinds of data sources available to us. And so there's a beauty to that. We can look at, so for instance, my team has looked at doing some work with Wi-Fi access point data, and what that means as far as engagement on campus. And then the last step is let's evaluate our models. And we do this on real holdout data. And usually, again, it's that temporal notion. So if you're looking to predict enrollment in the fall, then you train on historical years of data, and then you test it on a fall prediction that's realistic. And then we decide whether to move on to implementing this for student success. And that's where my expertise largely will drop off, right? That's where the bigger, broader interdisciplinary team needs to come up with the interventions, the mechanisms to actually do that. So there's a few challenges in this predictive models for student success pipeline. Building good predictive models really requires high organizational capacity. So there has to be an understanding of the outcomes that the institution needs to predict. So that means connecting across business units inside of the organization, the registrar, enrollment, alumni, student affairs, the individual colleges and units. So there's a lot of communication and overhead there, and that can be a lot of challenge to just come up with what are the reasonable things that we want to predict, because we want to actually change student success. Then we have the knowledge of how to build and evaluate models. And this I'm going to cast here as a data science or statistics problem. And that requires capacity, data scientists to do that. The ability then to execute on model building knowledge. And so here I've separated out the computer science programming aspect versus the data science statistics part. Now, computer scientists are involved in lots. I like to think we're involved in everything, but of course I'm a computer scientist. But I want to separate out the implementation of models into production, which is often done by what I would call a more traditional IT team, and the data science, which is often done by an academic analytics, business intelligence, changes depending on the institution. Then we need data which can inform the models. So it's not just data, but it's data which we think is related to the purpose of our student success prediction. Then mechanisms to intervene to change outcomes. This is actually several sub-bullets of points of different interactions. And then finally, the will to actually try and make changes that are involving predictive models. In this talk, and our work, we're really focused on trying to ameliorate some problems with these three specific steps: knowledge of building, ability to execute, and data which can inform on models. And I think that our work really contributes here. So I'm just going to take them kind of one after another. Knowledge of how to build and evaluate models. Data science, if you try to hire a data scientist recently, it's incredibly difficult. You'll get submissions, applications rather, for positions, but there's a lot of question about the skills and what kind of data scientist are they? What kind of data scientists do we need? And part of this is because data science methods and toolkits, approaches are just exploding. So David Donahoe wrote this great paper, 50 Years of Data Science, around 2016. I think it's published 2017, but it was kind of a white paper before that. I like to think 50 years of data science has happened since then. It's just been an incredibly fertile field, a lot of funding from all components, from academics, from government, from industry, and a lot of people doing activity there. data science is hard to do well. And part of it comes back to the hard to hire, and methods and toolkits are exploding. There's a lot of nuance to a lot of models, and we're constantly coming out with new kinds of models and new approaches. And I want to say the vendor secret sauce is questionable. It's not always bad. I don't want to cast it in that light, but I remember one very popular learning management system vendor was pitching some of their early predictive modeling work. Would have been about the time of course signals, so this is quite early, like 2010, and they were talking about how it was 95% accurate at predicting whether somebody was going to pass or fail a course. And of course, in many courses, if more than 5% of the people fail the course, that would be really dark. And so to get 95% accuracy, you just predict everybody's going to pass it. And that's not useful. I also have this little snapshot here from a course that I teach in. And this actually came up for one of the students from, and I did not turn this on, this was built into the system. This is the Coursera learning management system, but I teach in one of our degrees with that system. And it was a nudge that told the student, hey, if you complete this week 1 homework, it's going to make your completion likelihood 43% higher. There's so many questions that wrap up with this. The course has 4 weeks, and each one is equally weighted towards their grade. So if they don't complete it, they're definitely going to be in a bad position. I'm not sure there's any evidence that somebody didn't complete it and still passed the course, which seems weird. I'm not sure what they think the completion rate is, like how they measure that, because I don't remember telling them what the bar is to complete a course, and so forth. There's numerous ones. But the last piece of this knowledge about how to build and evaluate models that I want to call out is that nobody wants to be the university built models of student success on only one kind of student, put it into action, and it only benefits that kind of student. And we call that bias or fairness. And so really higher education needs a way to collaboratively build models that we trust and understand. The second kind of step here is the ability to execute. So a programmer is not a data scientist in general. Sometimes you can find unicorns that have both of these facets. Data scientists often don't focus on robustness. They don't do things like test-driven development, and putting models into production is often a detail for somebody else. So computer scientists and programmers are really needed in this mix to make production models. And the teams that exist have to incorporate various facets of the institution. And all of these are expensive and speak to organizational capacity. And so we really need to start thinking about well-specified software contracts for building and operationalizing predictive models of student success. And our work has some potential there to help with that. And then finally, data which can inform the models is a challenge. A good model needs good data. And so sometimes people ask, well, what kind of data do we need? What data do we need in those models? And so I started reflecting on this when, I did a quick poll of some of the data science folks around me, a review of the academic literature, which was really a reflection on my years of going to academic conferences about this. And definitely, without a doubt, there is a clear answer to this. All of the data. Everybody always says that. I want all of the data, all of it. I've never met somebody who's like, oh, I just want a little bit of the data, or I just need this one because it's got a clean signal. It's either all of it or what do you have, right? And so this is a challenge. And importantly, we're, as machine learning in social sciences is starting to grow more and more, we're seeing that we need data about the population that we want to help. And sometimes we don't have much of this. We need diverse data. So we need clean and reliable data about the diverse students that we want to help succeed. Okay, so with that, our team had a little conversation. It kind of went a little bit like this. Do you think we could just build a model at one institution and use it at another? And no, that's going to suck, right? Like institutions are different. Michigan's not the same as Indiana, not the same as UC Irvine, not the same as Michigan State. Now, these are all actually have some similar characteristics, right? They're all big public universities, but like, what about, we toss in Cornell, or we toss in Arizona State, or we start to look at all of these different kinds of universities. So then we thought, well, what we want that difference, right? Maybe we can make that an asset, not a liability. But again, like I can't imagine grabbing a model that was trained on University of Texas Arlington's data and just applying it at Michigan and expecting that it's going to work. So this one-to-one transfer doesn't seem like it's going to work. But then the question kind of kept bugging us. What if we just did that for a whole bunch of universities? What if we just wired them all up together? And so then we have a lot of students that the data is being trained on. We're not sharing data, we're just sharing these models. And so that got us working a little bit more and brought us to our approach, which in general is called model transfer in the machine learning area. So we start with this premise that sharing data is impossible and supporting diverse populations is our goal. Seems almost an intractable problem. Now, this of course isn't quite true. I think Unizin is showing some of this, but we also have projects like College and Beyond and College and Beyond 2. The UDW architecture is great. So there is opportunity to share data, but it's really hard. And certainly beyond the pay grade of a few of us faculty. But then we added into this a focus on the basics. Well, we're all US institutions, so we have IPEDS data, and we have to report that IPEDS data. So if we could get access to that and build models, at least we're talking the same language. We're talking about the same kinds of attributes of learners, even if we're actually measuring those slightly differently, maybe it's similar enough. We brought together 4 diverse US institutions. We decided we were going to build models, so we're going to use the same code base with the same prediction target. So in this case, in the data I'm going to show you here, it's retention to the second-year undergraduate from freshman or first-year undergraduate. We're going to use the same base data, IPEDS data. Now, we're actually using a subset of the IPEDS data because, frankly, we're researchers, we're not enrollment management or compliance or institutional analysis. So we don't exactly know what's all reported up in IPEDS, but we know some of the core things, and that was a good place to start. And so then we did it. We just went and built models for each of our institutions independently using the same code, the same kind of data, and the same kind of prediction. And then we just moved the model back and forth. And so here's the results of our first few transfer experiments here. We took these 4 different kinds of 4-year organizations: large public, an HSI, an online institution, or rather a portion of an institution that was focused only on online, and a private, a 4-year private. And there's a lot of differences between these. And so I'm not going to reveal which institution's which. We just got A, B, C, D here. But you can see that the number of instances that we train our models on varies between 1,000 and 30,000. So there was no requirement for it to be the same amount. We see that there's quite a difference when we look at the gender split. Now, most of this is actually a sex split as reported. So it's a binary value in the data that we have underneath. And then we wanted to capture something about some of the other demographic values as far as diversity. And so we took this underrepresented minority column. That's actually going to be important, and we're going to use that. And we can see that this one institution, 40% of their students were URM, whereas this other institution only 14%. So there's, some diversity aspects here. And we can see how that plays out again in this in the rest of the demographics with respect to both race and ethnic identities. And then different retention results. And we can see one university here, a 98% first-year retention. So like, what are their problems when it comes to predicting student success versus this institution? Now, mind you, that's a small n, but still 57% first-year retention. Even this one, 80% first-year retention. So there's some diversity here. Of course, it doesn't cover everything, but there's something. And we wanted to employ 3 different strategies with these models that we created. So the first one's called direct transfer. And this is the effect of using a different institution's model directly on my institution's data. So taking a model trained on Indiana's data and just bringing the model, those coefficients, we're using logistic regression in the data I'll show you here. It doesn't have to be, but it's just a bunch of coefficients. and applying it to the holdout data set at Michigan and making those predictions. And then we wanted to look at something called voting transfers. This is, in machine learning parlance, it's called an ensemble. And what's the effect of taking all of these other models? So let's say Indiana, Wisconsin, and Colorado's, and then sort of making a democratic vote between them, given my holdout data. So I'm not going to look at any of my own data and train my own model at Michigan. I'm just going to take these three. And we actually technically use something called soft voting, which is probability based. So we average the probabilities between these three and then use that to determine whether they're going to be at risk or that is not coming back the second year, or whether they will be successful. And then our last experiment here is called the stacking transfer. And this is also an ensemble method. So what's the effect of taking all of those predictions? So I've taken Indiana and I've taken Wisconsin and I've taken Colorado's predictions. I've predicted across all of my data, but then I also build my own model that includes those three features as well as all of my own iPad's data historically. So I can kind of see how those stack up and how much I can trust those. And sometimes this is called meta learning in machine learning. So here's an example. This is institution A. This is our real data for institution A. So the very first thing that we can notice is the black bar on the left. That's institution A, just the model as they would have done it themselves. And then these darker gray bars are the direct transfer bars. So institution B, and how well did that work for institution A? Institution C's model, and how did that work for institution A, and so forth. And the finding is really, compared to institution A's data, the other models underperform. Now, we expected this, but actually what we're surprised at is how close these models are. And this is interesting to think of when you think of institutions that don't have resources to model at all. Remember, we're trying to address some of these resources in the predictive modeling setup. And so if you could think of a low-resourced institution that doesn't have the capacity to hire data scientists, doesn't have the programming capacity, and so forth, in this case, they could just grab model C's, let's say they're institution A, they could just grab model C's, institution C's model, and it's not that far off. And there's a big discussion about metrics and what we're measuring. We're using area under the curve, which is, I won't go deep into it because it turns into a lecture, but it's a way to measure the accuracy or the fitness of a model that is generally reasonable, but there's a lot of nuance, and we can come back to that. Okay, so then the second thing we thought is, well, let's try this voting. So this is that soft voting. And we saw with this institution A that when we actually vote across the institutional models, we get something close to the best of all of them, but still this didn't beat our own model. So our own data was more expressive, at least for institution A, than it was to do this voting. But voting seemed to hedge against grabbing the wrong other institutional model. And of course, the exciting finding for us is that when we include other people's models with our own data and we decide to build our predictions, it outperforms that from ourselves. That is, taking other people's models, even though they don't have our students, still imparts some knowledge that our model fails to capture when we train it only on our data. And this suggests that we're picking up something that's more globally interesting, some measurement that's more globally interesting and available to us by collaborating with people. So that was unexpected, that we can improve our own models by including others, and that if we don't have capacity, we can actually get close by using the models of others. We're like, great, this seems wonderful. Seems like this is a success. And what's really interesting is then we applied this for all of the institutions, right? So we have, this is our target institution A, our target institution B, and these are all the models that we trained against institution B. And we actually see that there's differences, right, between these. And institution A was a bit of an aberration. In fact, one thing that was consistent across all four of these is that the stacked models perform very well. So the takeaway from that is there's a benefit to sharing for well-resourced institutions. Institutions that have the ability to build their own model can increase the quality of their model just by sharing the model, not the data, with other institutions. We also see that most of the time, the voting models performed at or above the best model that would be transferred. So more models generally means better predictions, and you can hedge against grabbing the wrong model by just taking a bunch of models and voting on them. And that's if you can't make predictions of your own. And then 75% of the time, the voting models actually perform better than our own data. Now, that wasn't true in the first institution that we looked at. Institution A is actually the only institution where this bar here, the voting bar, is less than the dark black bar. In all of these others, so institution B, their model performs worse on their own data than just grabbing all the data or grabbing all the models from other institutions. And that's true for institution D and institution C as well here. So institution A was a little bit unique in that case. And so this really kind of screams for sharing models of data, just these coefficients that have been trained. So it was surprising, the results of diversity, and we wanted to measure something called bias as well. And I'm going to skim through just a little bit of this, but the way we decided to measure bias is something called the maximum gap in AUC scores. And really, I wanted to demonstrate that if we have these 4 intersectional groups, and these are the 4 we used, so whether somebody is an underrepresented minority and man, or non-underrepresented minority and man, or woman and URM, non-URM and woman, what we measure is the maximum distance between the kind of min and the max. We want to measure that distance. And we intentionally don't correct for group size, because in a sense of diversity, it's not a correction. I mean, there are some utilitarian theories that would apply, that would say that you should adjust by group size, but I don't think that's the normal and well believed and practiced mechanism. So what does it look like? What do our models look like with respect to bias? So what we found is the use of other models, either voting or stacking, reduces the bias in the model. And here's an example of target institution A. But keep in mind, reducing bias is not the only thing we want to do. We also want a good model, right? One that has good fitness. So stacking seems like a clear choice here. And here's just a scan of how that looks across the different institutions. Consistently, a model trained at an institution has more bias than at least one of the models transferred from another institution. And most, 75% of the time, the stacked model has the least bias to it. And so I think what's interesting, there's a couple of things interesting here, but one is to look at target institution D, which has the most bias in the model that they train on their own data, which is really interesting, and how little bias there is when they look at the stacked model. And as we saw before, the stacked model also performs on average better. But there's also this institution C. What's going on here? Why is this stacked model so large in the amount of bias? And the answer is that it's complicated. I can't really dive into it in a short presentation, but would love to talk to people about it. The key is there's no well agreed upon standard of what fairness means. And so we're just looking at the size between, or the accuracy, the fitness rather, of this model between the minimum group and the maximum of these subgroups. But there's no standard for this yet. There's just a bunch of different ways of looking at it. URM and gender also are clearly socially relevant, but are these the only things that we care about as far as bias and fairness? And I don't think that's true. I think we care about things like first generation status, or maybe discipline-specific measures and so forth. But what seems clear is the takeaway coming out of this is that not all groups benefit, or at least they don't benefit the same from all techniques. So there's a plethora of limitations here. Is AUC something we care about? Is this AUC gap actually what we care about for bias? What about these different kinds of subgroups that I just mentioned? Why are we only using these 4 organizations? Is this an actionable model? These are all limitations and things that we either haven't been able to look into yet or intentionally haven't looked into. But there's a plethora of opportunities that come out of just these experiments. This is all just logistic regression. What if we tried different model types? What if we use something that's not just this basic IPEDS data? And what if we used our non-IPEDS data, our special sauce data that we have at different institutions? We're unique institutions, and we can do that with something like stacking, where we can use common models and we can use our own institutional data, and we showed that. We don't even train our models to minimize bias. We're just measuring bias in these models. There's a wealth of emerging machine learning work here. And what if we could scale this to Unizin data sets? And so that's why I'm here, really. That's why I was excited to put something in and share this work at the Unizin Summit. The unique model of the UDW means that this kind of experimentation can go on at a greater scale and much more quickly. No one needs to share their data outside of their organization. And in fact, they don't need a lot of these capacities because the commonality of the UDW means it's really as simple as running this kind of script code that we've written to do these analyses. And then the model just gets shared back as coefficients. I believe it's possible for our consortium to create accurate and fair models for the prediction of student success and to contribute these models to the world. And this approach can leverage our unique institutional knowledge alongside of our reference models, which have been trained on the combined history of millions of Unizin students. The potential to enable opportunities for under-resourced institutions by just giving them models. And if they can't afford to buy a platform, they can't afford to bring on teams. Think about community colleges, for instance. The potential to enable them to make reasonable predictions and build that into their workflow, I think, is immense. And on top of that, our efforts thus far are showing that this floats all boats. The well-resourced universities that can create their own models can improve them and reduce bias in them in general by participating in this. Okay, so that was longer than I was hoping to do, but I hope there's room for discussion. And I'm going to grab Ben's question. Feel free to ask questions however you want, but I'm going to grab Ben's question that was in the chat. So his question was, I'm sensitive that a large majority of the modeling work includes data preparation. So unless in institutions in Unizin, it's going to be difficult to transfer data preparation pipelines between institutions. And for that, I would actually say, Ben, that's why we chose IPEDS data, because everybody's got to report it. Everybody's got to clean that IPEDS data. So we think that that's actually the base, simplest data. Even before we go to the UDW, all of our work was on IPEDS data that which we all have to report up to the federal government. And so that's our starting point. And then I think the opportunity comes over to the UDW and the Unizin data platform, because then we can at least say within the consortium, okay, what do we want to take from this? And what do we want to train those models on and distribute those models? Now, one thing that's actually very challenging in machine learning is building pipelines that are robust to the loss of particular features, but are still useful. So in general, you train a model on a set of features. If those features change, you train a new model on that. And that means you're training a lot of different models. So that's definitely a place where we would have to look for more opportunities. But our goal thus far has been, first, let's deal with the most common data between institutions, so IPEDS and then maybe UDW, or maybe just iteratively grow on that. And then people can stack that with their own data if they have those capacities. I do think that if you have capacity to build your own models, you will always improve. That's what stacking showed us across at least these 4 institutions, that taking everybody else's model and your own data is better than just taking everybody else's model. But we're all better doing that collaboration. Allison asked a question. Are you noticing some emerging good practices when it comes to this kind of transfer learning? No. So in fact, transfer learning is relatively new. So it's being used in a couple of different domains. The one that I'm most familiar with it in is actually with deep learning. And with deep learning, you train, so image recognition in particular, you train deep neural networks to recognize, let's say, the difference between cats and horses, and then you chop off those labels, take a bit more data, feed it in. It's learning some things, like some things are small in pictures and fuzzy, and some things are big and have big eyes. And then you can use that to predict other things, like, I don't know, pelicans and guinea pigs. Two things, pelicans, I guess, I think have big eyes, and guinea pigs are small and fuzzy. And that seems to work fairly well. And so that's where a lot of the best transfer learning work is being done. But really in education, it's not being done. Instead, the focus is on building either parallel explorations, shared platforms, or trying to transfer data back and forth. And I think that this is a paradigm that we really should be starting to adopt and explore, because I mean, this is just for academics we were able to do it, which, and we're not sharing data. It's pretty remarkable. Right, so Anne Little asks the great question about bias. Bias is inevitable. I think that's awesome to know because it absolutely is. And have you had to explain to the users the limitations of predictive analytics? Yeah, so this is a huge translational research challenge, is how do you interact with putting these models into practice? And what I would say is actually there's very little work putting predictive models into practice in education. There's some dashboards, and I would say that in general, it's very simple there. I see there's a lot of research work being done to build those predictive models, but because we have these 6, 7, 8 steps, there's a lot of moving parts. It requires a big investment from an organization. So what we're trying to do here is reduce that, so that you could take an organization and you could say, hey, here's a bunch of models. We're pretty confident now that they've been trained on various different institutions that they're going to pick up a useful signal. Now go build interventions on these, build that political will at the institution, resource your advisors and give it a try. And as you collect data, we'll help maybe build that in, or maybe we won't. Maybe they never actually end up building models on their own data. But we could start to chop up the problem a little bit, and you don't have to have a team that's going to do everything from data curation through data prep, through modeling, through intervention and feedback loops, because those end up being multi-million-dollar investments for even simple tasks. Any other questions?
I think there was maybe one more question that might have gotten skipped from Jessica. Are there example interventions that are being identified as probably useful from looking at this data?
Oh, thanks. Yes, I did miss that. I apologize, Jessica. So actually, one of the things I'm gonna pull up, one of the things that is challenging to think about with this, that I think is also very interesting, is not on the intervention front, because we're not doing interventions. We have lots of thoughts on interventions, but actually I don't think we're the right people on those interventions. Somebody who has a better sense of causal factors is more likely to build, I believe, an intervention that's going to be impactful. That belief, frankly, largely comes from going to conferences and hearing computer scientists talk about interventions and sometimes mixing up correlation and causation and saying ridiculous things. But I do want to bring this image up, because this image, there's a lot in this image that I just didn't have time to unpack here. And the part that I'm going to try and unpack is that a model performs differently between groups. And we've chosen a specific metric to look at, this AUC gap. But the model the ordering of the groups, the people who are empowered in different models changes, and the accuracy, that is the fitness of the model, changes for those different groups as well. And so maybe we'll start by looking at this target institution D. We see here when D is trained on its own model, its own data, that one group at the very top, male URM students, has the highest fitness. In fact, it's almost perfect, which is astounding, which is great. But when we see the bottom group, female non-URM, it's below 0.5, which means it's worse than chance. It is a negative. This is horrific, right? Nobody would want to go with this kind of model for that group of students. That often gets lost when we talk about how well a model fits on using a unitary metric like AUC. And so we've decided to break that out. But we also see that not only is that bar smaller with stacked, but the ordering of the groups changes. And if you're in this group, male URM students, you actually see the accuracy, the fitness of the model, of the stacked model, decreases for that group, but it's made up for. And so the overall, the stacked model increases in fitness by raising all of these other groups. So that's a challenge, actually, when it comes to the interventions that we actually want to deploy, because it means that having an understanding of who the model is working for and who it's not working for, understanding the accuracy or the fitness of the model by these, in our case, intersectional demographic groups, is really important in understanding what you're going to do for the intervention. And here we're talking about retention into the next year after the very first year of university. And so I think that there's more causal pieces that we need to look at. For instance, first generation students. There's a lot of work that's been done showing the challenges there. And once you can start to form an understanding of those students, once you can predict those, at least you know the group, or you believe you know the group that you're going to intervene with. Once you can identify them, you might be able to identify the different aspects of that and start to lean in there on some of the implementation science. But it's not a predictive task anymore. Now it's a causal inference and trying to remediate there. I like Allison's question here, mostly because I take from it, she assumes I'm a data geek, and that's good because I teach data science. So at least I think that they would, I could tell my students that seemed to work. I would say that the problem with bias and fairness is everybody's got something in their head when it comes to bias and fairness, and there are no agreed upon norms. Again, when we look at gender, sexual orientation, and race and ethnicity. These are kind of four big targets that I think most of higher ed society in the United States agrees we should be looking to eliminate bias or eliminate model differences for. But I think that there are other groups that are interesting there. And there's always this question of, if you change aspects of your model to, or change aspects of your training process of the data and can reduce bias overall, or between your two maximum minimum groups, but it changes the impact for other people, what is the fair thing to do? What's the equitable or ethical thing to be doing there? I do want to be very clear, though, this is still emerging work, and we haven't even tried to make models that are bias-free. I mean, I think that'll always be, that's a journey worth going on, and we'll never get to the destination of completely bias-free, but we'll get closer. But we haven't even done that yet. Our focus has just been on evaluating bias, and by showing that you can take other people's models, other institutions' models, and you can stack it with your own data, that we can reduce the amount of bias, I think is astounding, right? It means that at Michigan, for a group of students we don't have, we can learn from UC Irvine, we can learn from Wisconsin, we can learn from Colorado's experiences with those kinds of students and reduce the bias and improve our overall fitness of our model, which is great.
We are at the top of the hour. So I want to give a big thank you to our speaker, Christopher Brooks. This has been very, very informative and exciting. We will be sharing the recordings and the live transcript, so be on the lookout for that. And I think we have one more session slot today for the summit. So I hope everybody enjoys, and I hope Zoom plays nicely for one more hour today before we can call it. Thank you all.
Everyone.